In this video, we will delve deeper into the MU Animation tab, building upon the information covered in the previous video. As a quick recap, in the last video we demonstrated how to animate moving objects on a station. To reinforce these concepts, we'll once more place a station into the frame. Then we right-click the station to open its context menu. Here we now can click on Edit 3D Properties or use the shortcut as you can see. Additionally, you can select the station and click on the spacebar to open the Edit 3D Properties dialog. Here we switch to the MU Animation tab. As demonstrated in the previous video, the MU Animation tab allows you to configure the animation of parts on material flow objects. When you click on Show, you can visualize the default animation path. Consequently, when you place a part, it will be animated along this defined path, as illustrated. Now we delete the default animation path. As we observe, the part is no longer visible. However, by examining the station's state, we can infer that it is in a block state, indicating the presence of a part. In essence, the part is physically located on the station, but isn't currently animated. The absence of an animation path on a material flow object results in mobile units being unable to animate along it. To address this, we click on Add to create a new animation path. In the dialog that follows, we are prompted to provide a name. For each material flow object, there must be a default animation path on which mobile units are animated. It's important to note that there's no need to manually enter default as the name. Instead, you can simply click on the three dots. These three dots are only visible when the default animation path has not already been created. In the dialog, you can then select the default. Upon revealing the animation path again, you might notice that it is positioned too high. This occurs because the animation path is generated at the center of the upper area of the bounding box, leading to the observed behavior. You can double-click on the cone and adjust its position by using the mouse wheel in the relevant coordinates. Please note that MU on the station is inherently animated in the conveying direction. If you wish to modify this, you can achieve it by rotating the cone. We've explored buffers in previous videos, and you're likely aware that parts in a buffer are typically stacked on top of each other. Nevertheless, this stacking arrangement might not always align with your specific requirements. Let's consider a scenario where we're operating in a glass factory and need to store glass vertically. In such cases, you have the option to customize the animation path within the buffer to accommodate these vertical storage needs. To showcase this, we insert a buffer into the frame. Next, we'll duplicate the part in the class library. For the duplicated part, we adjust the width and height to 1.5 meters, transforming it into a representation of a glass piece. We proceed by placing some parts into the buffer. As we can see, the parts are stacked on top of another. Then we open the tab MU Animation, show the animation path, and double-click the cone. Now we set the rotation axis to Y. Change the angle to 90 degrees. We then set the Z coordinate to 0.86 meter and the X coordinate to -0.94 meter. As shown in previous videos, we can use the mouse wheel in combination with the Shift and Control key to position the parts precisely. Now the glass will perfectly fit into the buffer. As demonstrated, the station animates just one part at a time. Let's explore the parallel station, which has the capability to animate multiple parts simultaneously. To do so, we insert a parallel station. If we now again open the Edit 3D Properties dialog and switch to the MU Animation tab, we can see that there is an animation area which is activated. So in the parallel station, we use an area rather than a path. We now place 3 parts on the parallel station. Then we show the animation area and move it higher by increasing the Z value. As we can see, the parts also moved up. The animation area operates automatically, arranging parts equidistantly in the XY plane. In the dialog, you can fine-tune settings for the animation area. Nevertheless, it's important to note that using the animation area is not necessary. To illustrate this, we hide and deactivate the animation area. As we can see, the parts are currently not visible because there is neither an animation area nor an animation path defined. To address this, we add an animation path and can see the 3 dots again. We proceed by selecting one of the 4 defined places based on the X and Y coordinates, with corresponding names shown on the right-hand side. Afterward, we create an animation path for the chosen place, click on Show, and then select the cone. We then can use the arrow keys to move the animation path to the desired position. You can follow the same process for the remaining animation paths. This approach allows you to arrange objects in a non-equidistant manner. If you prefer not to use the animation area, you can deactivate it and rely on the animation paths for each individual part. Now we want to have a look into length-oriented objects. So we place a source, a curved conveyor and a drain into the frame. Then we place a part on the conveyor and open the MU Animation tab. It's evident that there are no predefined animation paths for length-oriented objects, as their animation is internally generated based on their geometric characteristics, particularly along the curve of the conveyor. Nonetheless, it is still feasible to define a custom animation path. To initiate this process, we click on Add, and the familiar 3 dots appear. Upon clicking them, we can access the default path. We select the default option, create the path, and then display it. Then we take the second cone and move it outside of the conveyor. With the newly defined animation path, the part's animation will be relative to its position on the conveyor. For instance, if we consider the conveyor's length to be 10 meters and the part is located at 1 meter along the conveyor, the part will be animated along 1/10 of the length and will be visualized accordingly on 1/10 of the animation path. This implies that the animation path doesn't need to be as long as the actual conveyor length. It is simply scaled down to match the relative position of the part. Now we want to extend the animation path to showcase how the parts are animated. Then we can start the simulation. As you can see, the parts follow the animation path. Then we reset the simulation and delete the default animation path. We now want to show different path types. Therefore, we create a new one. In the path type, we this time select polycurve instead of lines. Now we are able to represent curved animation paths. So we show the new animation path and then click on Extend. Then we are able to use the Control key to place curves as we can do when inserting a conveyor. Then we again start the simulation, and as you will see, the parts follow the new animation path. Now we want to show the path type spline. Therefore, we again delete the animation path and add a new one. This time we select spline as path type. Then we again show the animation path. Here we now move the second and third cone. As you can see, we can generate a spline in this way. The last option in the animation type is rotation path. This is mostly used for camera animations. You could, for instance, easily create a round trip around the scene. However, we won't go in further detail at this point. To explain gravity mode, we insert a new conveyor with an incline. Then we place a source and a drain. Then we start the simulation without activating gravity mode. As you can see, the parts aren't placed perpendicular to the floor. Now we activate gravity mode, apply the changes, and restart the simulation. As you can see, in gravity mode, the part will always be placed perpendicular to the floor, either hanging from a rail or standing up on a rail. Now we set the height of the second anchor point to 1 meter. Now, let's commence the simulation, ensuring that some parts are present on the conveyor. Then, we'll look at the MU side to attach drop-down. Typically, moving objects are positioned flat on the conveyor, with the center of the bottom side of the objects connected to the conveyor's animation. However, if we modify this setting to left bottom and apply the change, you'll observe that the parts are now appropriately attached to the conveyor's left bottom, reflecting the adjustment. Furthermore, there's the option to establish an animation offset. By applying this feature, the parts will be animated with an offset relative to the animation path. To illustrate this, we configure the animation offset for the Y coordinate by setting it to 0.4. We then can open the dialog of a part and set the width to 1 meter. When we apply the change, we will see that the part will grow to the right. You might be wondering about the distinction between employing an offset and setting an animation path slightly higher. The key difference lies in the dynamic nature of these approaches. When you adjust the animation path to a higher position, it remains static. Therefore, if you were to alter the conveyor's length or introduce a curve, you would need to manually adapt the animation path accordingly. On the other hand, the animation offset is dynamic. This means you don't have to make any manual adjustments when you change the conveyor's length or incorporate curves into it. The offset adapts automatically to such changes, simplifying the animation process. Now we want to explain what can be done with the animation object in top of the dialog. To demonstrate this, we want to create a slider which moves the part into the machine. To do so, we insert a station into the frame. Then we open the station in a 3D window. Here we now insert a cylinder with radius of 0.1 meter and a height of 0.05 meter. Then we place the cylinder onto the station. We then right-click the cylinder and select Make Animatable Object. In the dialog, we enter Slider as the name and click OK. At this point, the dialog for the slider will appear. Within the Joint Settings group box, we can observe that the joint type is configured as a prismatic joint. Essentially, this indicates that the joint facilitates linear movement along the selected translation direction. Given that we intend to employ the cylinder as a slider, the current settings align with our requirements. We simply set a velocity of 0.1 meters for the desired movement. In the bottom, we can see that there is a preview translation box. In the value field, we could now move the mouse wheel to get a preview. As we can observe, the slider is currently moving in the X direction. However, if we adjust the translation direction to Y, we can witness how the slider's motion is oriented along the Y axis. We can observe that the reference point of 0 represents the middle of the station, which is where the processing takes place. -0.9 corresponds to the entrance of the station, and 0.9 designates the station's exit. Now, to ensure that a part can be animated on the slider, we need to create an animation path, and therefore we switch to the MU Animation tab and create an animation path. Within the dialog, we click on the 3 dots next to the path name. Since we are working on a station, there is one default animation path available for selection. This animation path will specify where the part is visualized, so we choose it and then show it. As we can observe, the animation path is generated at the center of the upper area of the bounding box from the cylinder. Then we hide the animation path again and close the dialog. Then we switch to the model frame and open the Edit 3D properties of the station. Here we switch to the MU Animation tab and designate the slider as the animation object. If we would not enter our animation object, then the animation would take place on the default animation path of the station. However, what we want is that the animation takes place on the animation path of the animation object, rather than the default animation path of the station. Up to this point, we have established a new animatable object that will serve as a means to transport parts. This approach allows us to model scenarios where specific actions, such as safety doors opening before a part moves to the slider for processing, can be represented. To model such scenarios, we have 2 options. The first method involves creating poses and then having the slider move to those poses. Alternatively, we can use coordinates directly. Using coordinates is preferable when the position where an object should move is calculated. An example of this scenario is the portal crane from the Cranes and More library, where the portal needs to be precisely positioned based on calculations or dynamic factors. On the other hand, poses are more suitable when you have a static and predefined position in mind. In cases where the object's location remains constant, poses provide a straightforward and efficient means of defining and managing these positions within the simulation. Let's begin with the creation of poses. To do so, we switch to the Poses tab and click on Add. We then set Entry as the name for the pose. Within the dialog, we proceed to select the animatable object for which we want to define a pose. As there is only the slider in this context, we select it. The presence of the bidirectional arrow indicates that the slider is configured as a prismatic joint, and therefore it has a defined translation direction. In case it were a revolute joint, we would observe a directed circle instead. Additionally, you can see the path and the range. Given that we know the precise position of the entry point, we can enter a value of -0.9 as it aligns with the position of the entry. If you use the mouse wheel for setting the value, you will instantly get a preview of the pose, else you need to press Apply to get a preview. We then click on OK and create 2 more poses for processing and the exit. Now we have created our poses. To use them, we can now add a source and a drain to the station. Then we create a pull control for the station. The station can be accessed over the anonymous identifier question mark. Before unblocking the part and enabling it to move to the slider, it's essential to move the slider to the entry pose we've defined. We have defined the pose at the station. To accomplish this, we first access the station. Since the poses are stored within the 3D properties of the station, we need to access these properties first. To do so, you can use the _3D notation. Then we can access the poses. Now we can use the Move to method. In the Move to method, we now insert the name of the pose. The Move method will return the time it takes for the animatable object to reach the specified pose. To ensure that we wait until the slider is in the entry pose, we can insert a wait statement before executing the Move method. Then we can proceed to unblock the part from the forward blocking list. Afterward, our next step is to command the slider to move to the processing pose. After the slider is in the processing pose, we can start the processing. Since we are starting the processing manually, we need to turn off automatic processing. This can be done in the dialog of the station. Now we switch back to our method and can save our changes. Next, we need to program an exit control. So we create an exit control. In the exit control, we first move the slider to the exit pose. Since the exit control is executed on the station, we can use the anonymous identifier question mark to access the station. Then we can use the same code as before. Do not forget to insert a wait statement in front of the Move to method. Then we can save our changes. If we now start the simulation, we will see how the slider is used as an animatable object to move the parts in the station. As mentioned previously, there is an alternative method for moving the sliders to a desired position, which involves using coordinates. So we again open the exit control. Here we now have to do minor changes. Since we want to move the slider to a specific position, we subsequently need to access it instead of the poses. And to access it, we can use the getObject method. As parameter, we need to pass the index of the object we want to access. Since there is only one object that we have created, we simply enter one. Using an index for performance is a more efficient approach, while an alternative method involves using the animation object's name, which, on the other hand, offers greater clarity. Then we again use the Move To method. However, this time we can enter a coordinate. Given that we now know that 0.9 represents the desired position of the exit, we can input that value. After saving these changes and running the simulation once more, you will observe that the program runs flawlessly. This concludes our video on an introduction to MU animation.